and welcome everyone, and thank you for joining today's presentation on temperature prediction models in Prosper, detailing rough approximation model. I am Mansour Zoidavianpour, and I'll be your guide through this insight on how this model works. Our journey will encompass a diverse range of topics, including understanding the rough approximation model, exploring sensitivity analysis with Python, studying the impact of U-value on well models using Prosper, comparing temperature models in Prosper, enhancing model accuracy through matching practice in Prosper, and concluding with key takeaways. Let's embark on this informative journey together. Okay, temperature prediction overview in Prosper. So we have three models in Prosper: rough approximation, enthalpy balance, and improved approximation. Each of these models, the characteristics of these models will be detailed out in the next slides. So here in the next three bullet points, as you can see, we are detailing out a U-value. So the U-value is crucial in temperature prediction because it quantifies heat transfer efficiency and guide design decision. Okay, so the U-values is entered in two sections in Prosper, in the surface equipment and also in the gradient in geothermal gradient section. So for the surface equipment is used to determine the heat exchange for equipment located above ground, specifically from the Christmas tree to the manifold. On the other hand, the U-value that key in the geothermal gradient section is employed to calculate heat exchange for equipments situated below ground, specifically from the Christmas tree downwards. So many factors actually influencing heat transfer, and there are some, for example, packer fluid properties, fluid characteristics, flow patterns, completion type, material utilized, and also the dimension of tubing and casing. So in this picture, as you can see, we can see the formation, we can see the cement and also the casings and tubing, and also the perforation and the fluid that enters the tubing. Here we can see the forced convection and also the free convection. So the difference between the forced and free convection, I hope all of you know, but I'm going to talk about it a little bit. So forced convection actually occurs when fluid motion is driven by an external force. As you can see here, there is a fluid that moves from the subsurface to the sand face, and from that to the tubing. So there is an external force. So in tubing, this means that the fluid is actively circulated or pushed through the tube by mechanical actually means. Free convection, on the other hand, relies on buoyancy force generated by temperature differences within the fluid. So in the annulus, free convection occurs when the fluid naturally rises or falls due to these buoyancy forces. Okay, let's review the basics of rough approximation model. So this is the model represented by several variables that included in the top right actually variables. So as you can see, we will start with the ambient temperature at point X. TAX represent the initial ambient temperature at any given depth within the wellbore, and of course it is influenced by factors such as initial conditions and the geothermal gradient. So the second formula is the rate of temperature change. The rate of temperature change denoted as dT over dx quantifies how fluid temperature changes with depth. It considers the overall heat transfer coefficient, fluid properties, and geothermal gradient. So for the third formula, which is the main formula to calculate the fluid temperature at depth x, Tx is the desired output, representing the fluid temperature at a specific depth. It is calculated by considering various parameters, including initial ambient temperature, geothermal gradient, U-value, and also pipe inside diameter, in addition to the initial fluid temperature. Okay, so in this formula, what we can see is that it's actually primarily deals with conduction and convection, and we are here to actually separate these terms. The first term is for conduction, that represents heat transfer through conduction along the wellbore. It considers the temperature gradient along with the depth, x minus L1, and the thermal conductivity, G2, of the surrounding material. Okay, so let's move to the second term. The second term actually is the convection. The term represents heat transfer through convection. It takes into account the heat transfer coefficient, U, which influences the rate of convection heat transfer. The greater the U value, the higher the rate of heat transfer through the convection. And also we have the third actually term, which is our advection. It accounts for heat transfer due to advection, which is essentially convection involving the bulk movement of fluid within the wellbore. It considers the effect of fluid velocity on heat transfer with higher U values leading to more efficient advection. So this formula combines both conduction and convection, making it suitable for analyzing temperature changes in a wellbore where heat transfer occurs through a combination of these mechanisms. Okay, so this slide is mainly shows the effect of U value on the output, which is the temperature, using this equation, which shown in the previous slide. We've used this equation and coded it in Python, and as you can see here, it clearly shows that increasing of U values will result in decreasing of the temperature. So the main takeaway from this slide is that as heat transfer coefficient increases, it signifies improved heat transfer efficiency within the system. And of course, operators can adjust the U value to regulate downhole temperature for various applications. And then balancing the U value alongside with other parameters such as geothermal gradient, fluid properties, and wellbore depth is essential. Of course, you can email me with this email address is located here, and then I will be more than happy to send you the code for you to do other sensitivities and understand actually the effect of several parameters on the output temperature in the wellbore. Furthermore, we've conducted several also analysis and changing the U values on a simple oil well model, and see the effect of such a change on the actually solution node temperature and also on the flow rate. And as you can see, we've actually plotted several plots here, each plot representing one U value. The first one is U value of 1, the second one is 5, the third one is 15, and the fourth one is 20. Okay, so this is all about U value. And then we've plotted also the solution nodes. As per you can see here, we have the liquid rate and we have the wellhead temperature. And as you can see, the lower actually the U value, the higher the wellhead temperature. So all these results have been actually evaluated, and all of these results performed in Prosper. And as you can see here, the solution node with increasing the U value will be decreased. That means that the liquid rate will be actually decreased with increasing the U value. Okay, so we've collected all the temperature models that are used in Prosper software and compare them here in this table. As you can see, we have rough approximation, enthalpy balance, improved approximation, and we have several characteristics that will be actually differentiate these kind of models. So that's why, for example, you can see that Joule-Thomson effects will be accounted for in both enthalpy balance and improved approximation. And for calibration, enthalpy balance does not require actually calibration. So there are, for the application, I give you an example about the steam. To model the steam effectively, a choice must be made between employing enthalpy balance, or opting for an improved approximation. The enthalpy balance actually involves the simultaneous solution for both temperature and pressure, in contrast to the actually rough approximation approach where temperature and pressure are calculated separately. Furthermore, the enthalpy balance always commences from known initial reservoir conditions and subsequently iterates to align with the user provided wellhead data, pressure and temperature. These often necessitates multiple iterations for each flow rate to attain convergence. These factors collectively elucidate why advanced thermal calculations employing a fully compositional fluid description tend to have longer computation times. So this is just an example to show you how this three temperature models can be accessed. So through the main menu, you can choose options, and from there you can go for the calculation type, and then from the model drop-down menu you can choose whatever actually model that you want to work with. Okay, so now in this slide we are going to apply some of our knowledge to solve some problems. So we've previously have actually modeled a naturally flowing oil well, but now it's time to fine-tune it. So after some production, you've tested the well, so you have well test data, and also obtained some PVD lab data. Okay, so here is the mission. So first of all, you need to match the PVD data with your model. That's why the accuracy of the PVT is crucial in modeling the well. So then we're going to scrutinize the well test outcomes and then refine our Prosper model to mimic the well test results, and then finally utilize the refined model to explore how change of certain variables, for example here tubing size and reservoir pressure, will influence the well performance. Okay, so data and procedures. So we have the PVD data, PVT table, well test data, and also the procedure that you need to follow in order to do matching. Okay, so here exactly you can see how this actually having a validated U value can affect our performance, specifically for the effect of the PVT, VLP, and IPR matching. Okay, hello everyone. We have an existing Prosper model, okay, and then the well is already producing for quite some time. And the new development is that we've tested the well, so we have well test data, and then we've conducted some PVT lab data. We already have some PVT tables, so it's good conduct to match the Prosper model with well test data and match also the PVT model. Okay, so in this case, what we are going to do, the first step is to make sure that all the actually correlation parameters are resetted. So in this case, we are going to reset all the parameters for the correlations. It's already reset, but we are going to do it based on the procedure that we are following up. After that, we need to match the PVT. So you remember that we've already provided some data for the PVT. So in order to access the data, we can access it through menu bar, PVT menu, and then input or double click in this page and then key in the data. So we have all the data entered here. In this case, we need to enter the PVT tables from this button. So we click it, and then we are going to enter the data. So we will start by Okay, done. So after that, we are going to click on done and then click on regression in order to do regression and come up with the best correlation that represents bubble point, GOR, or financial volume factor, and all viscosity. So now we are clicking on match all. Okay. After that, there will be a process, and then correlations will be automatically selected for each of these variables. So as you know, as you can see, Glasso is selected for bubble point, GOR, and information volume factor, and the Bell is selected for viscosity. So now what we are going to do, we just click on OK, done, and we've already done with this step. Okay, next step is to enter the well-test data. So from the matching menu, we are going to choose the VLP correlation, and then in this case, we need to enter the well-test data. Hopefully, I have this data here. I can simply copy and paste this data here. And after that, we are going to start with the left. So we have a task here that composed of several buttons. So we need to start from left as it appears in Prosper. We always start with the left and then move on to the right and from top to bottom. So in this case, we are going to estimate the U value. Remember that we've already in the U value, which was 8 into the geothermal gradient actually window. Here, based on the well-test data that is provided, Prosper is going to estimate a new U value and assign it to the geothermal gradient. So let's go on and let's actually click estimate U value. So in this case, you can see that the heat transfer coefficient is 8.07. So click OK, and then Prosper will ask permission to transfer this value to the geothermal gradient. Okay, so we click OK, OK, and then in order to double check this situation, let's click on done and then move on to this and then check whether yes, it's already transferred to the geothermal gradient window. So now what we're going to do is the next step, we need to do a correlation comparison, okay? In correlation comparison, what is normally done for oil wells is that we have two correlation, Fancher-Brown correlation and Donald-Ross correlation. So these two are considered the operating envelope of a tubing because one of them, which is actually the Donald-Ross give higher pressure drop and our Fancher give lower pressure drop. So in this case, we are going to use these two, for validation purpose, and use also several reliable correlations together with these two correlations. So in this case, as I said, Donald-Ross, Fancher-Brown will be selected. And let's select also Petroleum Expert 2, and then click on calculate. Okay, calculate. Okay, and then let's plot and see. Yes. As you can see here, based on this plot, our calculated actually VLP is far beyond our actually measured or test data. So in this case, we need to revise and actually revisit the PVT and other data in order to make sure that accuracy is there. So let's click on finish and done. And let's move on to the well test data. So all of us know that this well, actually the data from here, as you can see, input data, and then select the data, and then reservoir pressure is 4,000. And we all know that this bubble point pressure is 2,500, and then this well is already undersaturated. So based on also the data that entered here, we clearly see that the GOR actually in undersaturated phase needs to be actually maintained at 400. So now we are going to change this GOR in our well test and change it to 400. and then do the correlation comparison again, and then click on calculate, calculate, and then plot. Okay, as you can see, there is a good match for our multi VLP, and then okay, in this case we are going to finish. Click on finish, click done, and then go for match VLP. So we are just going with Petroleum Expert 2, and then click match, and then as you can see, we are having actually a good match for parameter 1 and 2. Both parameter 1 and 2 needs to actually the accurate the parameter it's near to 1. So in this case we are going to click on done, and then go for VLP IPR, and then calculate, okay, and then plot. And as you can see, there is there is 4% difference between the measured and calculated liquid rate. And this one for bottom hole pressure is about 0.9%. This is a good good results. However, we can further improve the results by going through the other steps. Okay, let's click on done, and then okay. Conclusion: the rough approximation model stands as a valuable, time-efficient tool widely utilized in wellbore temperature modeling within Prosper. While alternative models exist, their suitability hinges on factors such as accuracy requirement, computational efficiency, and data availability. Calibration and fine-tuning play pivotal roles in ensuring that temperature models align with real-world scenarios and yield dependable results. Our exploration underscores the significance of a nonsense approach to wellbore temperature modeling, where the choice of model aligns with specific project needs and objectives. Thank you very much for your attention.